Give the heading. Chapter 1,
Yes.
Basics of Thermodynamic. Give the heading. Chapter 1, Basics of Thermodynamic. Now, generally it is question
Yes.
1 from our exam. It is not a compulsory rule. Generally it is what? A question 1 from our exam. Huh? What is basics of
Okay.
thermodynamic? This chapter belongs to question 1 from our exam.
Okay, sir.
Given the
So
heading,
this is what formula based or a little bit concept based.
both, combination of both. But
Okay.
70% this see, this is the formula based also and concept based also, but here 70% is based on the formula and 30% is based on the concept here.
Okay.
Now in that, given the heading of this chapter,
Yes. Yes, sir.
now here the first point that we are going to study is what? The first point that we are going to study is a system. Give the heading system. Some people may say system, okay, whatever pronunciation you want, you can say.
Yes.
So give the first heading system. Now what is meant by system? We are going to first of all try to understand the system. System means what? It is defined as, see the meaning? It is defined as quantity of matter. It is defined as what?
Quantity of
Quantity of
matter.
matter or region in a space. I will explain you meaning of the word quantity of matter
Yes.
or region in a space selected for a study. So what is meant by system? It is defined as quantity of matter or a region in a space selected for a study. Now what is the meaning of word quantity of matter? Quantity of matter means what? Something which is solid or means we can see
Mass.
easily. Mass means it is a mass. Okay, it can be a liquid also. So suppose the screen in which means the currently I'm writing all these things on my laptop. So this laptop we can consider is that as a quantity of matter or a
Okay.
region in a space. What is the meaning of region in a space? Region in a space means what? A room currently I am taking this lecture. It is a region in a space. Or a building in
Okay.
which I am staying. It is a region in a space. So
Okay.
means whatever things we are indirectly, whatever things we are going to study, listen my words carefully, whatever the things we are going to study, that thing we call it as a system. Now there are two types of system. there are
Okay.
there are
Two types of system.
two types of system. First one is a closed system and second one is a open system. First one is what? Closed
Closed
system
system. Second
and
one is
second
open
one is
system.
what? Open system. Please write down up to this point.
Okay, sir. Completed, sir.
Okay. Now give the next heading. So we are going to understand what? Now give the next heading. Now we are going to understand what is meant by closed system.
Closed system. Okay.
Now From last 2 to 3 years, we are one familiar with one word, lockdown. Earlier days we used that word, we have heard that word in only in Hollywood movies. A lockdown means in Hollywood movie, suppose something bad happen in any organization, there is a word, a lockdown. We generally used to that word, we used to heard that word in only English movies, but now we are familiar with that word, a lockdown. What is the meaning of word lockdown? Lockdown means
Everything
what?
is shut down.
Shutdown means what? Nobody from inside going out, will not able to go out, or anyone can outside can come in. That is meant by word lockdown. So what is meant by closed system? Closed system means what? System, in closed system, mass cannot cross the boundary. What is meant by closed system? Closed system means what? In closed
Mass
system,
cannot
mass
cross the boundary.
mass cannot cross the
Boundary.
mass cannot cross the boundary of this system. Try to see the word. So what is meant by closed system? Closed system means what? Mass cannot cross the boundary of the system. It means what? What is the meaning of this one? It
Mass
means
cannot enter inside, not leave the system.
it means mass cannot leave the system,
Yes.
or
Enter the system.
mass cannot enter the system. So it means what? No one can come inside and no one can go outside. That is what see, mass can be anything. It can be liquid, it can be a gas, anything. Means a person, it can be. So that is what a mass. So means what we can say? Mass cannot, what is meant by open system? In other words, we can say mass cannot cross the what?
Boundary of the system.
So open system means what? Mass cannot cross the boundary of this system. So mass cannot leave the system, or mass cannot enter the system. So as it is, mass cannot cross the boundary means what? Therefore, for closed system, mass of the system remain what?
Constant.
That is the important thing. Mass of the system remains what?
Constant.
Remains constant. And one important thing we have to see, generally, try to see the understand this point. Generally, all the systems that we are going to study, all the system that we are going to study, generally all the system that we are going to study in this chapter, Santosh sir?
Yes, sir.
Generally all the system that we are going to study in this chapter are what?
Closed system.
Closed system. It means mass of the system remain going to constant here. See the scenario. So here
Yes.
in closed system, what will be the scenario? Important point. In closed system, mass of the system remains what? In closed,
Constant.
mass of the system remains what?
Constant.
Constant. Okay. So please write down this discussion.
Okay, sir. Done, sir.
Now the second type of system is what?
system.
Second type of system is what? Open system. Now in open system, what is going to happen in open system? In open
Mass
system,
may enter inside.
in open system, what we can say, mass can cross the boundary of this system. Mass can cross the boundary of the system. And what is the meaning of word mass can cross the boundary of the system?
Mass can enter the system or mass can leave
the system. Okay, so that is meant by mass can cross the boundary of this system. So please write down this one. Second term, open system.
Yes.
Here mass can cross the boundary of this system.
Done, sir.
Of the system here.
Yes. Alright.
Now try to see the scenario. Next is what? The next important point is what? Ideal gas equation. Next important point is what? Ideal gas equation. What is ideal gas equation? Ideal gas equation is what? PV is equal to mRT. It is the heart of this chapter. PV is equal to mRT. It is the heart ideal gas equation, or another name for the ideal gas equation is what? Perfect gas equation. Sometimes ideal gas we will call it as what? Perfect
gas equation.
So ideal gas equation or perfect gas equation, and it is equal to PV is equal to mRT. Now what is the meaning of each and every term? We will see. P basically means what? Absolute pressure. See, not only pressure, absolute pressure. Pressure with respect to zero line. What is meant by absolute pressure? All these things we are going
studied in the first time.
We are going to study in what? Hydrodynamic. So absolute pressure means what? So pressure with respect to zero pressure line. P absolute pressure in what? Unit will be, see the unit. Kilo Newton per meter square, or we will say what? Kilopascal. P stand for what? Absolute pressure in kilonewton per meter square or kilopascal. Then what is the meaning of V? V means what? Volume. Volume. What will be the unit of volume? In meter cube. Then M stand for what? Mass. In what? Kg. Then here is a new term. R stand for what? Gas constant. It is a constant for a particular gas. So gas constant in what? Kilojoule per kg Kelvin. See the unit. What is meant by R? R stand for what? Gas
constant.
And it is unit what? Kilojoule per kg Kelvin. So this is the new term. Then we will have what? Capital T. Capital T stand for what? Absolute temperature. So whenever we say absolute temperature, it unit must be in what? Kelvin. Capital K. Kelvin. Don't say degree Kelvin. Earlier days we used to say degree Kelvin, but now what we will say? Simply Kelvin. Don't say in degree Celsius. We can say degree Celsius, but here we will say only Kelvin. Capital K. If you are writing complete in detail, then in that means if you are writing Kelvin in detail, Kelvin unit, then here K must be what?
Capital?
No, K must be small, because here Kelvin is not a for us person name, it is a unit name. And whenever we are writing any unit name in detail, means in full form, then that first letter must be a small, normal, every letter in that one must be small. But if you are using abbreviation, then it must be what? A capital. Same for the Joule. If you remember, if we are saying Joule as a person name, then we know English thing is what? J must be capital O. Joule. It is a scientist. Joule is one of the scientists. He has done lot of work in the field of thermodynamics. But if we are using a unit Joule and we are writing in full form, then that J must be in what? Small. If you are using an abbreviation, then it must be what? Capital J. That is the basic thing for any unit. Same for the Newton also. If you are using abbreviation as a person, means as a unit, then capital N. If you are in full form of the unit, Newton, then n must be what here? This n must be what? Small n.
Small.
Same for the Pascal. Kilo Newton meter square or kilo Pascal. See the things here. So before going further, please write down this one. Ideal gas equation or perfect gas equation.
Perfect. Done, sir.
Now the next thing is what? Ideal gas. Give the next heading. The next point that we are going to study is in what? Ideal gas or perfect gas. Give the next heading. Ideal gas or perfect gas.
Okay, sir.
Now what is meant by ideal gas or perfect gas? Ideal gas means what? A gas which obeys. What is the meaning of obeys? A gas which obeys ideal gas equation
Yes.
or perfect gas equation. Ideal gas equation or perfect gas equation, same meaning. A gas which obeys ideal gas equation or what?
Perfect gas equation.
A perfect gas equation is called an, what we will say? Is
We
called
want to
an,
say it as an ideal gas or a perfect gas.
we will say ideal gas or what?
Perfect gas.
Perfect gas. Ideal gas or what? Perfect gas. So please write down this discussion. Ideal gas or perfect gas.
Done, sir.
Now, what are the examples of ideal gas or perfect gas? Examples of ideal gas is what? Air, oxygen,
Okay.
we denoted by O2. Oxygen molecule is denoted by O2. Then helium, we denote by He. Okay, scientific name. Then
Okay.
carbon dioxide. How we denote carbon dioxide?
CO2.
CO2. Carbon dioxide is denoted by CO2. Then we will have a what? Carbon monoxide. How we
CO.
denote carbon monoxide? We will
CO.
denote carbon monoxide by what? CO. Then methane. How we denote methane? We denote methane by what?
CH4.
CH4 and etc. So these are the few examples. We will see more examples of. So generally how to identify means generally how we can consider. So at room temperature and room pressure. At room temperature and room pressure means atmospheric pressure. If that thing exists in a gas form, see this one. Vapor, steam vapor means steam. Water vapor, we can't consider it as an ideal gas. because at a room
Okay.
temperature and room pressure, it is not exist in a gas form.
Yes.
It is exist in a high temperature. But generally, the substance which exists at a room temperature and room pressure in a gas form, generally we will consider it as an ideal gas. Generally, that is the,
Okay.
so here oxygen, helium, carbon dioxide, carbon monoxide, methane, all these things at a room temperature and room pressure, both condition, not only room temperature. See, if you observe
Okay.
CO2, we know dry CO2.
Yes.
Dry CO2 means we will say dry ice.
Right.
Okay, means what? Dry ice means what? It is a basically solid CO2. But in
Yes.
that case, it is, though it is at a room temperature, but what is the speciality of that one? It is at one, it is in highly compressed form. But in that case, we can't say it as a ideal gas. So
Okay.
means dry ice we can't say ideal gas, though it is a CO2. So CO2 in what? Normal atmospheric pressure and temperature condition, that is what we will say, that is an, we will consider it as an ideal gas. And what is
Okay.
ideal gas? Ideal gas means what? Gas which obeys this ideal gas equation or perfect gas equation. So please write down these examples. Now try to see the scenario here, what we have to do and how we are going to approach the things further. See the things here carefully, what we have to do and how we are going to approach the things further. Give the next heading, gas constant. How we denoted gas constant, can you tell me? How, what is gas constant and how we denote gas
Capital R.
constant?
Capital R.
Capital R. So we denote gas constant by what? A capital R. And how we will
Yes.
say, how we will write down expression for capital R? Capital R is equal to what?
PV
RO,
by MT. Okay. Okay.
RO by what? Capital M. This is a capital M. Huh? Sometimes some people may say small m and for capital M, for them it is the same. No. This is what? A capital M. RO by capital M. Or we will say RU by what? Capital M. What is the unit of R? Can you tell me? What is the unit of R?
Unit of R is kilojoules per kg Kelvin.
Unit of R is what? In
Kilojoules
kilojoule
per kg Kelvin.
per kg Kelvin. Okay. Now we will see, try to understand the meaning of each and every term here. So what is meant by RO or RU? Sometimes in few questions of exam they denote RO or RU. Sometimes they use RO, sometimes they use RU, and both meaning is the same. RO or RU means what? Universal gas constant. RO or RU means what?
Gas constant.
Universal gas constant, and its unit is what? In kilojoule per kilomole Kelvin. It is a constant volume. Generally, if you see the exam question, 1 minute, I'm going to show you one exam question. See this one, question number 21 from our booklet, or it is asked in July this exam. See this one, July 2015 exam question 1.
Yes.
If we have seen this question, what does we come to know that from this question, from this July 2015 exam question? So see, RO universal gas constant, here we they denote RO universal gas constant by what? Universal constant by what? RO, and its value they have given us what? 8.314. So what is the value of RO? So see,
8.314.
8.31, 1 minute, I have made the mistake, 1.3145 kilojoule per kilomole Kelvin. Okay, so this is what, and then what is the meaning of capital M? Capital M stand for what? Molar mass. We will not go to the unit of molar mass, we will not go that much detail. Just say capital M stand for what? Molar mass. Please write down this discussion. Completed?
Yes, sir.
Now the next we will take a one example. With that example we will try to see the okay. We are going to try to find out what our target is. What we are going to take a example for CO2. Now
Okay.
if you have seen this question, what they have given us, relative atomic masses of a CO2. So what then, relative atomic masses for carbon, how much they have given? 12. For
12.
oxygen 16. See this one.
16.
For what? For carbon 12, oxygen 16. So in this case, if you observe the scenario, so atomic mass for carbon, how much they have given us? Atomic mass
12.
for carbon,
12.
for C, it is a C stand for carbon, and atomic mass for what?
Oxygen is 60.
Atomic mass for oxygen is what?
60.
60. So therefore molar mass, and how we denote molar mass? Molar
Capital
mass
M.
for CO2 will be what? We will denote by capital M. So 1 carbon in CO2, 1 into 12. And how many oxygen? 2 oxygen,
2.
2 into
Yes.
16. So what will be the value of capital M? It will become for
32 plus 12, that is 44.
oh, so how much it will become? 12 plus 32, 44. Don't worry about its unit. And what will be the R? It will be what? RO,
8.315.
RO by capital M. So RO is
Okay.
what? 8.3145
45.
divided by what? 44.
44.
So if you do the calculation, what is the value of R we will get?
Yes.
Please do the calculation with me.
It happens to be, sir, 0.1848. 0.1848.
I have made the mistake here. 8.314. I have made the mistake 8.3145. So it must come 0.18896 kilojoule per
Perfect, sir.
kg Kelvin. So in this way we got a value of R. Please write down this discussion.
Yes, sir.
Give the next heading, specific heat. We generally denote specific heat by small c.
Okay, yes.
Give the next heading, specific heat, and we generally denote specific heat by what? A small c.
Yes, sir, done.
Now what is meant by specific heat? It is defined as, see this one, it is defined as amount of energy required. See this one, it is defined as amount of what?
Energy required.
Amount of energy required for
Raise it.
1 kg mass amount of energy required for 1 kg mass to change its temperature by what?
1 degree Kelvin.
1 Kelvin. To change, it is defined as amount of energy required for 1 kg mass to change its temperature
by 1 Kelvin.
To change its temperature by what?
1 Kelvin.
1 Kelvin. So what is meant by specific heat? We have a 1 kg mass, and if you want to change its temperature, change of temperature by what? 1 Kelvin, then that amount of energy we will say it as what? A specific heat. So what is meant by specific heat? Specific heat is defined as amount of energy required for 1 kg mass to change its temperature by what? 1 Kelvin. Now there are two types of specific heat. It is a constant for a particular and ideal gas. First type of specific heat is what? C must be small. C suffix V. This V in suffix. So CV stand for what? Specific heat at constant volume. Okay. What is meant by CV? CV is what? Specific heat at constant volume. And for a particular ideal gas, value of CV is a constant. So it is a constant for a particular ideal gas, specific heat at constant volume. Unit will be in what? C. Amount of energy. Energy unit will prefer here kilojoule. For 1 kg mass. So per kg. And by 1 Kelvin. So unit will be in what? Kilojoule per kg Kelvin. See the unit. Another type of specific heat that we are going to use here. It is also an constant for a particular ideal gas. Specific CV, specific heat at constant
pressure.
CV constant volume. CV stand for what? Specific heat at constant volume. Then by default we can guess CP stand for what? Specific heat at what?
Constant pressure.
Constant pressure. So it is a constant pressure. Whatever may be the process, the value of CV, CP will remain constant for that particular ideal gas. So specific heat at constant pressure. See the things here. Please write down this discussion about specific heat. Now the next term that we are going to study is a adiabatic index or isentropic index.
Okay.
Next term that we are going to study is what? Adiabatic index or isentropic index. We will see why we have given this name adiabatic index or isentropic index in upcoming discussion. So adiabatic index or isentropic index, and it is denoted by what? A gamma. How we denote? Gamma. This is what? A gamma. This is not a R. So gamma, adiabatic index or isentropic index, it is denoted by gamma. And gamma is equal to what? What will be gamma? Cp by Cv. Gamma is equal to what?
Cp by Cv.
Cp by Cv. So please write down this discussion. And also write down this relation. Cp is equal to what we can say? Gamma Cv. Give the next heading. Relation between Cp, Cv, R and gamma. See, these are the four constants for a particular ideal gas. Whatever may be the process, remember this point, Cp, Cv, see this one, huh? See these points, Cp,
Yes.
Cv, R and gamma, these four are a constant for a particular ideal gas. Means whatever, whether it is a constant pressure process, constant volume process, constant temperature, constant entropy, whatever may be the process, or polytropic process, whatever may be the process, these four things are constant for a particular ideal gas. Cp, Cv, R and gamma, these are the constant for a particular ideal gas. Huh? So it doesn't depend on a process of that particular ideal gas. Huh? It is independent. So these are the properties, and properties are independent. So Cp, Cv, R and gamma is a property of a particular ideal gas. It is independent of the process. We will give the note after this discussion, but remember this point. So now what you have to do, so what we have to understand here, we have to memorize this relation. We will not go to into derivation. Cp minus Cv is equal to what? R. Cp minus Cv is equal to what?
R.
R. So we will say Cp minus Cv is equal to R. Now just few minutes before we have seen Cp is equal to what? We have seen gamma Cv. So can we
Yes.
replace Cp by what? Gamma
Gamma
Cv.
C.
Can we do this one?
Yes, sir.
Just now we have seen. I will write down
Yes,
here
sir.
also. We are going to replace Cp by what?
Gamma CV.
Gamma Cv. And we can take out Cv common here.
Yes.
So what will remain inside the bracket? Gamma minus 1
Yes.
equal to R. So what Cv will become here? Cv will become what? R by what?
Gamma minus 1.
R by what? A gamma minus 1. So this is another relation.
Yes.
And just now we have seen. Okay. So please, up to this point complete, and then we will see our upcoming discussion.
Okay, sir. Just give me a minute.
Now try to see the scenario further here. What we can say? So we have seen Cp is equal to what we have seen? Gamma Cv.
Yes.
So can we replace here Cv by what? R by gamma minus 1. So
Yes.
what we will say? Cp will become what? Gamma into R by what?
Gamma minus 1.
Gamma minus 1. Please write down this relation. Now we will write down the note. What note we will see? What just now few minutes before explained? Cp, Cv, R and gamma are properties of an ideal gas. It is independent. These properties are what? These properties are what?
Constant.
This are properties of an ideal gas. These properties are constant for an particular ideal gas, and it is independent of what? What we will say? independent of the process.
Okay.
And these properties are, you got the meaning of these properties are
Independent of the
process. Okay, whatever may be the process. See, in this chapter we are going to deal with 5 processes. First, constant volume. Second, constant pressure. Third, constant temperature. Fourth, constant entropy. And fifth, polytropic process. So whatever may be the process, Cp, Cv and R is a constant for a particular ideal gas. And these properties are independent of
the process.
Whatever may be the process, these 4 properties are fixed.
Okay, I'll just note it down. Done, sir.
Give the next heading. Internal energy. And we are going to denote internal energy by capital U. Give the next heading.
Okay.
Internal energy. And we are going to denote internal energy by what? Capital U.
Yes, sir.
Now, what is meant by internal energy? It is defined as energy of the stationary fluid. Energy of the what?
Stationary fluid.
Fluid. So what is meant by internal energy? Internal energy is defined as energy of the stationary fluid. Now what is meant by fluid? Fluid means what? Fluid means what? Either liquid or gas or vapor. So it is defined as energy of the stationary fluid. And you got the meaning of word fluid? Fluid stands for what? Means thing which can flow. What is the basic meaning of fluid? So liquid can flow, gases can flow, vapor can flow. So these are the meaning of what? A fluid. But solid, can we say solid as a fluid?
No.
So now then how we denote? See this one. There is one more thing. Change in internal energy. How we denote change in internal energy? We denote change in internal energy by what? Delta U, and change means what? Final internal energy minus initial, and its unit will be what? In kilojoule.
Kilojoules. Perfect.
Please write down this relation. So this is what? A change in internal energy, delta U.
Nice.
Now suppose we want to find out change in internal energy. Suppose our target is what we have to find out? Change in internal energy of an ideal gas. Whenever we want to find out change in internal energy of an ideal gas, then that change in internal energy will become what? Delta U will become what? M CV T2 minus T1, and its unit will be what? In kilojoule. So this is the relation for whenever we want to find out change in internal energy of an ideal gas, means delta U, U2 minus U1 of an ideal gas, then that relation we will become what? MCV T2. This is the generalized one. Change means what? Final minus initial. But that final minus initial for an ideal gas will become what? MCV T2.
MCV T2 minus T1.
And what is the meaning of CV?
CV is a specific gas constant.
Specific
At
heat
constant volume.
at constant
Specific
volume. What is meant by CV? CV stand for what?
specific
Specific heat at
heat
constant volume.
volume.
Please write down this one. Now the next term that we are going to study is enthalpy, and we are going to denote enthalpy by what? A capital H. Go give the heading enthalpy, and enthalpy we are going to denote by what? Capital H.
Okay.
Now what is meant by enthalpy? Enthalpy means energy of a
Fluid.
flowing fluid,
Flowing fluid, yes.
river water,
Yeah,
flowing
kinetic
fluid,
energy and potential energy to be
neglected.
not considered, neglected.
Enthalpy means energy of a flowing
Fluid.
fluid. Enthalpy means energy of a flowing fluid. If we neglect
Kinetic energy and potential energy of the fluid.
kinetic energy, if we neglect kinetic energy and potential energy of the fluid. And what is meant by fluid? We already explained. The thing which can flow. Solid, liquid, vapors. These are, we can say it as a
Yes.
enthalpy. Please write down this definition. So enthalpy
Yes.
means what? Energy of flowing fluid. Try to see the scenario. Mathematically, enthalpy means what? Mathematically, this is the only mathematical definition. Mathematically, H is equal to what? Capital U. Capital U stand for internal energy, P stand for pressure, and V stand for volume. So mathematically, enthalpy is equal to enthalpy H is equal to U plus PV, and its unit will become what? Enthalpy, it is a energy, so it is basically become again kilojoule. Here we will prefer kilojoule because joule will become what? A smaller unit. Change in enthalpy means what? Can we say how we denote change in enthalpy?
Delta H.
We can denote change in enthalpy by what? Delta H. And delta H
Yes.
means what? H2 minus H1.
H1.
H2 means what? Final. H1 means what? Initial. And its unit will be what? In kilojoule.
Kilojoules.
So that is what? A change in enthalpy. Now suppose if you want a change in enthalpy of an ideal gas. Suppose if you want change in enthalpy, this is the generalized expression. Enthalpy means final minus initial. And if you want
Yes.
final minus initial for an ideal gas, change in enthalpy of an ideal gas, then that change will become what? Change in enthalpy of an ideal gas. For ideal gas, delta H will be equal to what? M Cp T2 minus T1, and unit will become what? In kilojoule. So please write down these relations.
Okay.
For a change in internal energy, mCV T2 minus T1. Change in enthalpy, mCp T2 minus T1. Try to understand the difference here.
Okay. Change in internal energy is M into CV.
Yes,
And
change in internal energy is what? M into
M
CV.
into Cp.
And change in enthalpy, mCp. But it is for an ideal gas.
Okay, sir. So above one internal gas also was for ideal gas. Sir.
What?
Change in internal gas, that is delta U.
Change in internal energy for an ideal gas.
For an ideal gas, yeah.
That is what we have written. Change in internal energy of an ideal gas.
Yeah,
Change
yeah.
in enthalpy of an ideal gas.
Change in enthalpy.
So this is the expression.
Into Cp T2 minus T1.
Now we are going to study a new term here. First, give the next heading by red pen. First law relation for closed system. To the next heading. First law relation for a closed system. Give this heading. Now, what is first law relation for a closed system? Try to listen my words. First law, remember, this relation is valid only for what? Whenever our system is what? Closed system. So, first law relation for a closed system, and first law relation for closed system is what? Q minus W is equal to what? Delta U. We will see meaning of each and every term. So, Q minus W is equal to delta U, where Q is a new term for us. Q means what? Heat transfer.
Heat transfer.
What is meant by Q? Heat transfer. Unit will be in what? Kilojoule. W stand for what? Work done. And it is also in what? Kilojoule. And delta U, just now we have seen change in internal energy.
Change in internal energy.
And it must be also in what?
Kilojoules.
Kilojoule. Please write down this discussion. So here every term is in what? Kilojoule.
Yes, sir.
Make the underline to this one Q. Q is what? A heat transfer. That is what first time we introduce word Q. That is heat transfer.
Yes, sir.
Now the next thing will be what? Sign convention.
Okay.
Give the next heading. Sign convention. Subheading. Sign convention for Q. Give the next heading. Sign convention for Q. Q stand for what? Heat transfer. If you will get a value of Q positive, if you will get a value of Q what?
Positive.
Positive. It means what? Heat
Q is
addition.
added.
Heat addition to the system.
Yes.
Heat addition to the system, or in other words we can say heat input. Heat addition means what? Heat is coming into the system.
Yes.
Heat input to the system. If you are saying Q negative, what we will say? If we will say Q negative, it means what?
Heat is removed.
Heat rejection.
Heat rejection. Okay.
Heat rejection by the system, or heat rejection from the system, or heat rejection means what? Heat is going out. So heat output from the
system.
So please write down this sign convention for Q.
Okay, sir.
Next, give the next heading.
Yes, sir.
Sign convention for W. So what is the sign convention for W? Here we are going to deal with two things. If you will get a value of W positive, if you will get a value of W is what?
Positive.
If value of W is positive, then it means what? Work output from this system. Work output from this system, or work done by the system. And when we will get a work done by the system? Whenever there is a expansion, see the wordings. Whenever there is a what?
Expansion.
Whenever there is a expansion is there, in that case we will get what? Work output. In that case what we will get?
Work output.
Okay.
Positive.
In that case, we will get what? Work output. We will get what? A work output. Whenever we will get a W negative. So what is meant by W negative? Work input to the system. Work input to the what?
System.
Work input to the system. Or what we will say? Work done on this system. And when we have to do the work on this system? Whenever we are doing the compression. So work output we will get in case of expansion, and work input when we have to do work on the system in case of the compression. Means compression will not happen automatically. Suppose this is what our piston cylinder, our arrangement. Try to see the scenario here. Suppose this is what our piston cylinder arrangement. 1 minute, I will draw the proper piston cylinder arrangement. So this is what our cylinder, and here I am showing you a piston. This is what a piston. This is what a piston. So in that case, what is, so if you are doing the what? A compression here. So what is going to happen? Suppose compression means what? What we have to do? We have to give what?
Energy, work.
Work input. Then and then compression will happen. So piston will go up. So that's why here a negative. So please write down this discussion. In case of compression, we have to give a work input, means we have to move the piston up. So for moving the piston up, what we have to do? We have to give the work input, and that is what we will take work input as a negative in our sign convention. Give the next heading.
Yes, sir.
Entropy. Entropy we are going to denote by what?
S, capital S.
We are going to denote entropy by what? A capital S. Now what is meant by entropy? Entropy is defined as, try to see the scenario. It is defined as degree of randomness. Degree of what? Randomness or disorder.
Okay.
Degree of randomness. What is meant by entropy? Degree of randomness or disorder. And unit of entropy is what? Unit of S.
Kilojoules per kg.
Unit of entropy is what? Unit of S. Only entropy is kilojoule per Kelvin. Kilojoule per Kelvin. We will see the specific entropy also in upcoming discussion. But now, just now we are seeing entropy. Unit of S is what? What is the unit of S? Kilojoule per Kelvin. Capital K.
Done, sir.
Entropy of the system. Try to see the next point. Next point is very entropy. Very interesting. Entropy of the system. Entropy of the system can be changed by following two things. Can be changed by following two things. So what will be our first thing? Entropy of the system can be changed by following two things. What will be our first thing? Try to understand the meaning of first thing. Can be changed by following things. First thing is what? By heat transfer. By what?
By heat transfer.
Okay. In heat transfer we will have two things. One is what? Heat addition. So by heat transfer means what? By Q. So in heat transfer we will have two things. One is what? Heat addition, and another one is what? Heat rejection.
Heat rejection.
So entropy of the system is changed by two things. One is a heat transfer, and we will say another thing also. So first thing is one heat transfer. We will have in heat transfer also two things. So due to heat addition, entropy of the system is going to increase.
Increase.
Due to heat
Heat
addition.
transfer and
So in heat
heat
transfer,
addition.
maybe heat addition or heat rejection. So due to heat
Yes.
addition, what is going to happen? Due to heat addition, entropy
The
of the
entropy of the
system.
system will increase.
Due to heat addition, entropy
Of the
of the
system will
system.
increase.
The system will increase,
Yeah.
and we will see how high it is going to increase. And in B point, due to heat rejection, in first point A and B, due to heat rejection, what is going to happen? Opposite to
Entropy
the
of
heat
the system
addition,
will decrease.
entropy of the system what?
Will decrease.
Entropy of the system will decrease. So first way of change in heat transfer means change in entropy is what? Change in entropy is what? First is what? Heat transfer, and second thing is
Yes.
what? By irreversibility.
By irreversibility, correct.
And what is the meaning of
Friction.
irreversibility?
Friction. Example is friction.
Example of irreversibility is what? Example of
Friction.
irreversibility is what? A friction.
Yeah.
Example of irreversibility is what? A friction. Due to
Yes.
irreversibility, entropy of the system, what is going to happen? Due to
Increase. It is
irreversibility,
going to increase.
due to irreversibility,
The entropy of the system will increase.
due to irreversibility, entropy of the system, entropy of the system will always increase.
Yes.
Means due to friction, what is going to happen? Will
Entropy
always
will increase.
increase. Always increase. So
Yes.
due to friction, what is going to happen? Entropy of the system will
Will
always
always
increase.
increase. Yes, sir. Done.
Now how the heat transfer is going to happen? Means see, we have seen, see the example of classroom. Try to see the things here carefully. How the heat addition going to increase the entropy? Suppose there is a one classroom.
Yes.
Here I am taking a lecture, and there are
Yes.
60 students in the class. Just imagine,
Yes.
class is fully packed with the number of students is what? A 60 student. I'm taking a lecture in a what? A peak summer. What I'm doing?
Yes.
I'm taking a lecture in what? A peak summer. So this is what? A board, whiteboard, in which I'm taking a lecture. So in peak summer, what is going to happen?
The temperature will increase inside.
Okay, so what is going to happen? We will see. In peak summer, suppose in peak summer in central India or in North India, what is going to happen? Anywhere in India except few places, what is going to happen? A surrounding temperature is what? Higher, and room temperature is
Yes.
as compared to lower. So what is going to happen? A surrounding heat is going to enter into the what? There is a heat addition. Q addition is there.
Yes.
So
Yes.
whenever there is a heat addition, what is going to happen? What is going to happen? Everybody in the
Increase.
classroom, what is going to feel? They are going to feel uncomfortable due to heat addition, because surrounding
Yes.
temperature is higher, room temperature is lower. Because of that, what is going to happen? Everybody in the classroom is going to feel uncomfortable. Means teacher is not able to take a lecture properly. Students will not able to, whatever the things teachers said by the teacher is not going to see the things properly, means listen the things properly. So everybody is feeling what? Uncomfortable. Means everything is in what? Classroom random or disorganized. Things will not organized because of the what? Teacher will not able to teach properly. If teacher will not able to teach properly, student will not able to listen properly. So everything in the classroom will become what? Due to heat addition, disorganized.
Disorganized.
And disorganized means what? Not properly organized. Means things are what? Random. So due to
Okay.
heat addition, what is going to happen? Randomness of the classroom is going to increase. And increase in randomness, what is the meaning of entropy? We have seen meaning of entropy means what?
Increase.
Degree of randomness or entropy. So due to heat addition, what is going to happen? Randomness of the classroom is going to
Increases.
increase, and due to randomness, entropy of the classroom is going to increase. So
Yes.
due to heat addition, that's what we have seen. Due to heat addition, entropy of the system will always increase. Now the next thing, suppose we are, instead of hot classroom, we are providing AC to the classroom. Suppose some
Yes.
few colleges provide AC also. So in AC, air conditioned classroom, what is going to happen? Heat is going to reject from the classrooms, and things are what here properly
Organized.
organized. And if the things are properly organized, means what? Here randomness, in case of heat addition, randomness is going to increase. So if the things are properly organized, means what? Things are not random here, means
Yeah.
properly organized, not random. So it means what happened to the randomness? What
It
happened to the
remains
randomness?
constant.
Randomness is going to what?
Decrease.
Decrease. So due to heat addition, entropy of the system is going to increase because disorganized or randomness is going to increase. And due to heat rejection, what is going to happen? Things will become properly organized. Now,
Yes.
okay, so you got the meaning of heat addition, means heat addition, entropy of the system. Due to heat addition, entropy of the system will what? Due to heat addition, entropy of the
Decrease.
system will increase. Due to heat rejection, entropy of the system will decrease. So that is what the example of classroom we have seen. Now then what is
Yes.
going to happen? Due to irreversibility. See, now the best example of irreversibility is the naughty student in the class. What is the best example of irreversibility? Best example of irreversibility is what? Naughty student in the what?
Yes.
Naughty students in the what? A class.
Class.
So
Yes.
best example of irreversibility is what? A naughty student in the class. So if you want naughty students in the class, suppose there are some naughty students in the class, then what is going to happen? Whether we are whether we are keeping them in hot classroom, means heat addited classroom, or air cooled classroom, what is their task?
To disturb the class.
To disturb the class. So due to that naughty students, what is going to happen? Entropy or randomness or disorganizedness of the classroom, what is going to happen? It is going to
It is going to
increase.
increase.
So naughty student means what? Naughty student is nothing but the irreversibility of our classroom. Means if you consider this classroom as a system, if you consider what, guys, everyone, if you consider what? This classroom as our system. So due to that naughty student, what is going to happen? What is going to happen? Entropy of the system will going to what? Increase.
It
So
will increase.
it will increase. So this is what this is all about entropy. So here in two ways we can change the entropy. First is what? Heat transfer. Due to heat addition, entropy of the system will increase. Due to heat rejection, entropy of the system will what? A decrease. By irreversibility, entropy of the system will always increase. Now the next thing is what? Isentropic process. Give the next heading. Isentropic process. Give the next heading. Isentropic process.
Yes, sir.
Now what is meant by isentropic process? The process in which what is meant by isentropic process? The process in which entropy of the system, entropy of the system remains constant. What is meant by isentropic process? The process in which entropy of the
system
remains constant is called an isentropic process. What we will say is called an isentropic process. So entropy of the system, what happened to the entropy? It is going to remain what? Constant. Entropy of the system remains constant. Now entropy of the system remains constant means what? S is equal to constant.
Yes.
Or what we will say? S is equal to constant, or we will say initial entropy is equal to what? Final entropy. That is what we can say. Initial entropy is equal to final entropy, or what we can say? Change in entropy means what? Final
Zero.
minus minus initial, it will become what? A 0. So in 3 words we can say this is what meant by isentropic process. Please write down this discussion, isentropic process.
Done, sir.
So this is what a isentropic process. Now after isentropic process, there is a next process is what? Reversible process. Isentropic process, or next process after isentropic process, reversible process. The process in which, try to see the scenario, what is meant by reversible process? The process in which irreversibility is 0. What is the example of irreversibility? The process in which irreversibility is what?
Zero.
That is no
Friction
friction. That is no friction. The process in which irreversibility is 0 is called what we will say?
Reversible process.
Is called reversible process. The process in which irreversibility is 0 is called reversible process. And important thing is what here? One important note that we have to understand here. So what is important note here? All the processes in this chapter, see, what is meant by reversible process? The process in which what? What is meant by reversible process?
Irreversibility is
0. So I will write down here irreversibility, that is irreversibility is equal to what? 0. And one
Yes.
important point that we have to understand here, all the processes, see this point, very very important point, all the processes in this chapter, all the processes in this chapter are reversible processes. What?
okay.
All the processes in this chapter are what?
Reversible processes.
Reversible processes. Therefore, what we can say? Therefore, what we can say here? All the processes in this chapter are reversible processes. Therefore, entropy of this system. Therefore, entropy of this system in this chapter. Therefore, entropy of this system in this chapter is only changed by what? Who is responsible then? See, I told you what I told you. What we discussed, entropy of the system is changed by two things. First thing is what?
Heat addition or heat removal.
First thing is what? Heat transfer. In heat transfer, two things are there: heat addition, heat rejection. And second thing is what?
Irreversibility.
By irreversibility. Now, if there is irreversibility is 0, then entropy of the system is changed by what? Therefore, entropy of the system is in this chapter, entropy of this system in this chapter is only changed by what?
Heat transfer.
Is only changed by what? Heat transfer. In heat transfer, it may be heat addition or it may be a heat rejection. So please write down this discussion. Please write down this discussion. Reversible process and note related with this chapter. Now give the next heading. Adiabatic process.
Adiabatic process.
Give the next heading, adiabatic process.
Yes, sir.
Now what is meant by adiabatic process? The process in which, try to understand the meaning of adiabatic process. The process in which heat transfer is 0. What is meant by adiabatic process? The process in which
the heat transfer is 0.
Process in which heat transfer is
0.
0 is called an adiabatic process. That is what we will say. That is what we can say.
Q is equal to 0.
That is what we will say. Q is equal to 0. Please write down this discussion. Now, just now we have seen what we have seen. All the processes in this chapter are what? Reversible processes.
Reversible process, yes.
Okay, all the processes in this chapter are what? Reversible processes. It means entropy of the system is what? Only changed by what?
Constant, and it will be changed by heat transfer.
Is only changed by what? Entropy of the system is only changed by heat transfer. That is what we have seen. Now, for adiabatic process, what is the heat transfer is what?
0.
So then, what will be the change in entropy here? Tell me. What will be the change in entropy for adiabatic process in this chapter?
It will be also 0, so constant.
It will be 0.
Yes.
So, sorry, what will be the change in entropy for this one? For adiabatic process, it is 0. Change in entropy will be 0 and entropy remain what? Constant. Try to understand the scenario here.
Yes.
Since all the process, or we will say as all the processes in this chapter, as all the processes in this chapter, as all the processes in this chapter are reversible, since all the processes in this chapter are reversible, as all the processes in this chapter are reversible, so and entropy of the system, what we will say, or we will say, it is not a proper word, 1 minute. What we will say, see, adiabatic process for this chapter, see, try to see the scenario here. What we discuss, if you want to change entropy, if you want delta S not equal to 0, if you want delta S equal to 0, then two things must be 0. Q must be 0 and irreversibility must be what?
0.
And for adiabatic process in this chapter, both is happening now.
Yes.
So what we can say? Adiabatic process in this chapter, what we will say? Adiabatic process in this chapter, also called adiabatic process in this chapter, also called isentropic process. Why we will call isentropic process? Can you tell me?
Yes, because the enthalpy remains, entropy remains constant throughout the system.
Adiabatic process in this chapter also called isentropic process because here irreversibility is 0.
Yes.
Because here irreversibility is 0 and heat transfer
remains constant.
And heat transfer also 0. And heat transfer also 0, means no heat addition, no heat rejection. Therefore, no change in entropy. Therefore, no change in I'm talking about change in entropy. I'm not saying entropy never be 0. There is only one case entropy is 0. That is third law of thermodynamics. That is not related with our syllabus. So we are going to deal with only two laws, first law and second law, but we will not see that laws. We also don't need that from exam point of view. But entropy, for us, entropy never be 0, but entropy change. So therefore no change in entropy. Therefore no change in entropy for an
adiabatic process.
So adiabatic process in this chapter also called what? What we will say? Adiabatic process in this chapter, what we will say? Also called isentropic process. And why we will say isentropic process? Because here irreversibility is 0 and heat transfer also 0, because the name itself saying adiabatic.
Yeah.
So heat transfer is 0 because irreversibility is 0 and heat transfer is 0. So therefore no change in entropy for an adiabatic process. Please write down
Yes.
this note. So remember, whenever we say isentropic, we will say isentropic throughout this one, it has a two meaning. Entropy change 0 and heat transfer is 0. That is the two meaning. So isentropic
Okay.
process we will also called what? Adiabatic process, or adiabatic process also called isentropic process. So we will say vice versa, both the process. Adiabatic process means isentropic, isentropic means adiabatic, only for this chapter. And why is it like that? Because here two things for the, because the main important things in this chapter is what we have assumed, irreversibility 0 means no friction here. Because
Yes.
of this term, because of what? Because of this term irreversibility is what? A 0. Because of this term we can consider like this. So please write down this note.